here. So that's a pleasure for me to have that's a pleasure for me to have Federico speaking this week and next week too, by the way. And he will discuss about several papers he did, and which are totally related with our project EcoDep. So, Federico, thank you for accepting to give all those talks. Thank you.
Okay, thanks to you, Paul. So, first, thanks to all to attend this seminar. Let me also say that I am Federico Maddanu, and I am a postdoc researcher at the University of Cergy under the EcoDep project of Professor Paul Jucan. So let me say also welcome to Marina Frederick, that she joined now to our seminar. And I think her presence here is very important because this paper is strongly correlated with one of her research. So today we will discuss a time series analysis on ethane abundance in the atmosphere. Well, the present work, let me say, that is a work in progress. And it is carried out along with the collaboration of Professor Tommaso Proietti from the University of Torre Vergata. So, let's start by saying that understanding ethane dynamics is of crucial importance in the context of climate change, since ethane affects the distribution of ozone in the troposphere. I recall that the troposphere is the lower part of the atmosphere, and even though we know that the ozone layer protects the life in the planet from the solar irradiation, we also know that the formation of ground level ozone has a pollution effect on the air quality and damage ecosystems. On the other hand, the ethane is an indirect greenhouse gas in the sense it survives in the atmosphere for only about 2 months, but it affects the atmospheric lifetime of methane that in contrast is a direct greenhouse gas that survives for a longer period in the atmosphere. Basically, ethane emissions can be used as a measure of methane emissions. Since methane is released in the atmosphere by both natural events and anthropogenic activities, while ethane emissions do not have significant natural sources, then we have that monitoring ethane levels becomes crucial to have an idea of what is the human contribution to the abundance of methane in the atmosphere. Well, according with the main literature, ethane emission in the northern hemisphere may be mostly attributed to the production and transport of oil and natural gas. According with the estimate in Helming et al. 2016, we have the natural, biogenic, and the biomass burning accounts for about 22% of global ethane emissions, against the remaining 78% attributed to anthropogenic activities. Well, an increasing on ethane trends has been found in the troposphere in the period from 2009 to 2011, to 2015, with a reversal after some decades of declining. This declining was due to the regulation policy versus the main anthropogenic emitters. Then in 2015, we observe a hiatus in the ethane growth, whose nature may be only temporary and still need to be fully understood. In our study, we investigate on the ground-based Fourier transform infrared solar spectral measurement of ethane abundance in the atmosphere recorded at 6 ground stations that are both from the northern and the southern hemisphere. So we will consider measurement taken in the North American continent with the Toronto and Chile ground station, and in the, let's say, Euro area with the Izana and the Dark Spitze station. And we also consider two records from the Australian continent in the southern hemisphere. In this slide, I just plot our ethane time series that will be investigated. So what we can immediately observe from this time series is that we have a strong seasonal behavior at the annual frequency, since ethane degrades faster in summer with high temperatures with respect to cold weather conditions. This implies basically that the time series are typically characterized by peaks in winter time, generating a sort of seasonal heteroscedasticity. Well, another characteristic of this time series is that we have a huge percentage of missing data that account for about 70% for each time series. Finally, we have that the high persistency of the annual cycle and the elevated percentage of missing data makes the detection by visual inspection of a hidden trend component a very difficult task. As you can verify by yourself, it's very difficult to guess some sort of trend dynamics behind this data. So we will see how our approach is able to solve this issue. Well, let's now discuss some previous studies in the literature about ethane time series. Well, this previous study shared the main approach in treating the ethane cycle as deterministic and proceeded to remove it by regressing the data on a sum of sinusoidal terms. The analyses were then carried out on the residual of such a regression by, for instance, by splitting the samples in the 2 time periods and fitting a linear trend on both the subsamples in order to detect change in the trend direction. Then also some kind of bootstrap procedure is applied to obtain the confidence bands of the trend component. Well, according with a paper of Federico et al. 2020, the author point out that this linear approach may obscure important characteristics in the data, such that they propose a nonlinear and non-parametric model where the estimation of a nonlinear trend component allows to capture much interesting features from the series. Well, we will see that how our approach is able to do the same. So first, let me say that in our opinion, in contrast with the previous study in the literature, there is no reason to treat the ethane cycle as deterministic. Since ethane depends on annual temperatures, it is known that phases and amplitudes of global temperatures are varying over years. This is why we suggest to model the cycle as stochastic, imposing the fundamental frequency and the harmonics fixed at the annual frequency, while we let the parameters regulating the phase and the amplitude of the cycle, we let them to evolve stochastically according to independent fractional noise processes. Basically, using a model that has been introduced recently by me and Professor Tommaso Proietti, and that is called the fractional sinusoidal waveform process. Our model also allows for the possibility of a deterministic cycle as a limiting case, such that the nature of the cyclical component can be suggested by the inference on the model parameters. Finally, the trend component is modeled in our approach by a standard random walk. This is at the end the model that we use for fit the ethane data. Basically, we have that xt is the log transform of the ethane time series. Here, the log transform is used to mitigate the heteroscedasticity in the data. And basically, we have a standard trend plus cycle model where the trend follows a standard random walk with the disturbance ZT. And the cyclical component psi-t is given by the sum of m fractional sinusoidal waveform process, which basically which are given by psi jt, And basically they define a stochastic sinusoidal wave in which the parameters that regulate the phase and the amplitude that are AJT and AJT star are basically time varying and are led to evolve according to two independent fractional noise processes, where the error term presented the same variance sigma square j eta. And basically, if we have that the DJ parameters belongs to the open interval 0, 1/2, then we have that each one of the psi-JT component exhibits long memory under stationarity. Basically, the idea is that the cycle component is disturbed at each one of its hem harmonics by a fractional sinusoidal waveform process with long memory. The assumption of our model are completed by assuming that the sources of disturbances that are ZT and eta JT and eta JT stars are assumed to be mutually independent. So each psi-JT component present so spectral density according with the equation 2, which result to be unbounded at the frequency lambda times j in the case the process is a long memory. And it also presents a closed form for the autocovariance function given by equation 3. So let me also specify that our process, our fractional sinusoidal waveform process allow for deterministic cycles as a limit case when both the sigma square j eta and the dj parameters approach to 0. In fact, if we consider the harmonic process ZT, where now the parameters that regulate the phase and the amplitude are not time varying, but are just two high ID normal variable with the variance sigma square JA, such that the autocovariance function of ZT is given by sigma square JA times cosine of lambda JK. Then we see that rearranging the equation for the variance of the sigma square j eta parameters, we see that as dj go to 1/2 from the left, then the autocovariance function given equation 3 of the psi-JT component, it approaches in this case to the autocovariance function of the harmonic process ZT, such that basically the harmonic process is just, and so the deterministic cycle is just a limited case of our process. We can also see that in this case, the spectral density of the process is discrete, such that the spectral density of the cyclical component f psi that is given by the sum of the spectral density of the singular psi-JT components may present mixed spectra. In the sense we have both continuous and discrete spectra. Well, also due to additivity and independence between the error stem, we have that the autocovariance function of psi-t can be derived according with the equation 4, where the parameter sigma square psi-j is equal to the product between the sigma square eta j times this ratio between these two Euler gamma function. In such a way, the total variability of the process of the cyclical component that is gamma psi 0 is equal to the sum of the m sigma square psi j parameters, allowing for an easy decomposition of the total variability of the cyclical component in the single contribution of each one of its harmonics. Well, so by looking into our main model in equation 1, we can see that we can derive a state space representation of the process xt. Using the following measurement equation and the state equation in equations 5, where where alpha t plus 1 is defined as the state vector, where the first two components are basically the trend component and the cycle component. The parameters that you see to appear in matrix G, T, and H that are basically the sigma tilde parameters and the phi tilde PJ parameters are obtained by are obtained via the Darwin-Levinson recursion by considering basically an autoregressive of order P representation of the cyclical component psi t. I recall that the Darwin-Levinson algorithm is a tool that allows us to compute the inverse of a Toeplitz matrix, and in our case, it allows to solve the Euler-Walker equation by using the autocovariance function of psi t as an input, according with the proposition 8.2.1 in Broccoli and Davis in 1986. Then estimation and prediction of xt can be carried out via the Kalman filter, according with the system of equation in 7, which computes recursively the innovation Vt. Okay, where basically it computes this innovation iteratively for t equal to 1, 2 to n, where n is the sample size, and where alpha t given t minus 1 is the expectation of the state vector, pt given t minus 1 is the conditional variance of the state vector, where the filtration ft minus 1 is here to consider like the information set available since time t minus 1, and ft is the conditional variance of xt. Kt, on the other hand, is known as the Kalman gain, and it is basically what the Kalman filter learned from the current observation at time t. The algorithm is initialized via the two equations in Hecht, where mu0 comes from a representation of the random walk process, and gamma psi n is a p by p matrix, in which the high j elements are equal to gamma psi in equation 4. Okay, so in order to obtain the estimates of the parameters, we proceeded to maximize the quasi-log likelihood function given by equation 9. Let me stress that here we speak about a quasi-log likelihood function because what we are estimating is an approximation of the model xt, because we consider an autoregressive of order p representation of the cyclical component. The resulting quasi-maximum likelihood estimator, theta hat n, which maximizes Ln, has been proved to be consistent and asymptotically normal distributed by Chan and Palman in 1998 in the case of a standard long memory process and under stationarity. It's of course it to be useful for our paper also to prove the consistency and the asymptotic distribution of theta hat n under our model, where in contrast with the Chan and Palman 1998, we have non-stationarity at the long run frequency. So we can also obtain via this methodology an estimation of the trend and cycle components, for instance, by computing via the Kalman filter the real-time estimates of the state vector that are obtained according with the equation 10 by considering all the information available since time t. And we can also compute the smoothed estimates of the state vector according with the system of equation 11, in which we consider all the information available in the sample by computing the formulas in 11 via a backward recursive pattern. Okay, starting from t equal n since to t equal 1. Well, so let's now discuss how we handle the missing data problem that we have in our series. I recall that in the ethane series, we have a large amount of missing data that account for about 70% of the total observation. So in our case, we deal with the missing data problem by defining the partially observed process yt equal xt times ct, where XT is the process of interest that we defined before, that is assumed to be independent from CT, and which is not completely observed. And CT is a binary process that is equal to 1 if XT is observed, and to 0 if XT is missing. The parameters estimation and the prediction of XT in the presence of missing data is particularly easy via the Kalman filter methodology. Indeed, in this case, we handle with the missing data problem just by skipping the updating operation in the Kalman filter, for which at the t iteration for which CT is equal to 0, such that in this case we computed the Kalman filter only according with the equation 12, where basically we do not compute anymore the Kalman gain. Basically, we do not compute anymore the KT component in this equation. This is because the KT component basically is represent what the Kalman filter learn from the current observation, and if the current observation is missing, then the Kalman filter cannot learn nothing. Similarly, we also computed the real-time estimate and the smoothed estimates of the state vector according with the system of equation in 13 and 14. Well, notice that at the moment we do not make any assumption about the missing data generating process CT. Let me say that investigating on the dependent structure of a CT may be of some interest, at least for simulation purpose. Since CT is directly observable in real-world time series, we know that missing observations do not appear randomly in time, but often follow some serial correlation pattern. This is because the observational process depends on both the interaction of several variables, which can be both completely random or not. For instance, if we look to our empirical illustration on the ethane time series, and we plot the correlogram of the empirical missing data generating process CT, we see that in these correlograms we are very far from the assumption that the CT is an ID Bernoulli. For instance, in the case of the Thule and the Wollongong series, we find a sort of decreasing in the correlograms. And in the case of the other series, we find a sort of seasonality at the weekly frequency. So this is why we suggest to model this serial correlation pattern via the following process given in equation 15, where basically we model the conditional probability of CT given CT minus 1 as a logistic process. The idea of modeling the missing data generating processes in this way comes from a suggestion of Lionel Fouquet, that is a researcher from Rennes that is also involved in the CODEP project. So thanks to Lionel for this idea. Here we have basically that the argument of this logistic function, that is KT, follows a standard seasonal autoregressive process, which exhibits seasonality if S is greater than 1, such that if S is equal to 1, then we have that KT is a standard autoregressive over the 1 process. If S is equal to 7, then we have that the conditional probability of CT present a sort of seasonality in its correlograms. Epsilon T here, notice that is a martingale difference sequence. And also notice that if both beta and rho are equal to 0, then we have that CT is basically an high ID Bernoulli random variable with a probability given by 1 over 1 plus exponential of minus delta. So let's now see how all this theoretical framework works in a simulation exercise. So we now generate the partially observed process YT, where XT is generated according with our main model, and the CT is generated according with the process in 15. So we set here the true values of the parameters of the XT process. Notice that we set the variance of the the variance of the random walk component of the trend component very low, sigma z, with respect to the variance of the cyclical component that are sigma square j eta. The reason is that we want in this simulation exercise that the trend component result to be very hidden from the data. And the detection of this hidden trend component is the main purpose of this exercise. So finally, we consider two possible scenarios for generating the missing data generating process CT. In the first scenario, we set S is equal to 1, such that CT follows a logistic autoregressive over the one process. And in scenario 2, we set S equal to 7, such that the CT exhibits a seasonality at a frequency 2 pi over 7. The idea is to reproduce the correlogram of the empirical missing data generating process in the ethane time series. So here I show you the plot of our simulated time series. Along with a correlogram of the missing data generating process CT. We see that in scenario 1, CT follows a sort of geometrical decreasing in the correlogram, and in scenario 2 we have a sort of seasonality at the weekly frequency in the CT process. Notice also that it is not easy to detect by visual inspection a trend dynamics behind this simulated data. And by implementing our approach with a Kalman filter, I will show now how we are able to detect the real trend dynamics that are behind this data. So in this plot, basically we have that the red line is the true trend component, and the dashed green and the blue lines are respectively the real time and smoothing estimates of the trend component. In the bottom panels, we have basically the same series, but we add the dotted green lines confidence bands of the real-time estimates that are obtained via the Kalman filter. So basically notice that our estimates are able to capture the main dynamics of the trend components. And also notice that the real trend component lies almost totally inside the two confidence bands. So basically, this result suggests us that our model is able to capture the real characteristic of a trend component when it results to be hidden by both high persistent cycles and a large percentage of missing data. Well, let's see now how all of this works in the empirical application on the 6 ethane time series. So let's start by analysis, let's start our analysis by investigating on the periodic structure of our ethane time series. Here I plot the Lomb-Scargold periodograms of the 6 series. Let me recall that in contrast with the standard periodogram, the Lomb-Scargold periodogram can provide us the periodic pattern of a time series, also when this time series is not totally observed. In fact, this technique is common, for instance, in astrophysics, in the study of the time series of light curves of young stars, where usually the time series are not completely observed or equally spaced. So by looking into this periodogram, we immediately see that all the series present a strong periodicity at the annual frequency. And so almost the persistency in the data is concentrated in the fundamental frequency of the annual cycle. But also we have some persistency in the, let's say, 3-4 first harmonics of the annual cycles. Well, this suggests us to specify our model 1 in the following way. So we set the fundamental frequency lambda equal to the annual frequency, and so on the successive harmonics. we set arbitrarily the number of harmonics as m equal to 12. And we truncate the autoregressive representation of the cyclical component as p equal to 100. Well, the choice of these two parameters, m and p, is arbitrary. Basically, we found that allowing for a higher value of m and p does not change the result in a remarkable way. But let me say that also if we allow for a lower value of m, like m equal 10, then basically we do not change too much the result. So here I show you the parameters estimates relative to the first three harmonics for each one of the 6 time series. I do not report the estimates of the successive harmonics since they appear to be not too much significance, in the sense that the variance parameters that measure the contribution of such harmonics to the persistence of the cycle result to be very close to 0. From these estimates, first we noted that the variance of the trend component sigma z result to be very lower with respect to the variance of the first fundamental frequency of the cycle, and we also noted that almost all persistency in all the series is concentrated on the first harmonics, where we estimate a memory parameter dj hat very close to the non-stationary threshold of 0.5. We also test these DJ parameters to see if it is equal to 0.5 by testing the null hypothesis DJ is equal 1/2 by using the Robinson 1994 test for non-stationary long memory process. And we reject the null hypothesis that DJ is equal to 0.5 for all the series. We also find that the sigma eta 1 parameters is greater than 0. Sorry, here should be not sigma z, but sigma eta j. So this is a typo. Basically, I recall that in the case that dj is equal to 0.5 and d eta j is equal to 0, then this is the limited case of the deterministic cycle. Then basically these estimates suggest us that the cycle in ethane is not deterministic, but is a stationary stochastic cycle. This is the main result that we can obtain from that is suggested by these parameters estimates. Well, here I show also the residual diagnostic in terms of the periodogram, correlogram, histogram, and cuckoo plot of the residual. So we can observe that we find almost weakly correlated residual, suggesting us that our model provides a good fit. We also do not find a very significant residual periodicity for almost all the series. And of course, you can complain that the distribution of the residual is not exactly a normal. Of course, we can observe a sort of leptokurticity and of asymmetry in these histograms and in these cuckoo plots. That is probably due to the fact that our model is not able to remove completely the heteroscedasticity in the data. But let me say that I believe that it will be very difficult to obtain a result that is better of this one in terms of residual diagnostic. Well, via our methodology, we are also able to extract the smoothed estimate of the cycle components that are plotted here for the 6 series, and also the main output of this paper that are the smoothed estimates of the trend component that I show here. Well, basically what we can observe from this smoothed trend is that basically we have a sort of common behavior in the northern hemisphere ethane trends. So basically we support was already reported in the literature on ethane trends that we observe a growth in the ethane trend between 2009 and 2014, with a successive pause close to 2015 in the ethane series. Well, this support the idea that the trend dynamics in the northern hemisphere are driven by the production of oil and natural gas in the United States. In this slide, I show the monthly time series of the crude oil production and natural gas extraction in the United States. And we can observe the same dynamics. We have a trend that increased between 2009 and 2014. And we have a successive pause in 2015. Well, it should be also interesting to consider the production of natural gas in Russia. Because I recall that the United States are the top leader producer of natural gas in the world, but the Russia is to the second place. But let me also say that the production in the United States is 50% more with respect to Russia. And also, let me say that I checked the time series. I do not report here, but I checked the time series of natural gas production in Russia, and it do not present a peak close to 2015. Well, this supported the idea that is also reported in the ethane literature that the main driver of the ethane trends is the production of production in the United States. Well, let's say something also about what happens in the southern hemisphere. So if we consider here the Lauder and the Wollongong ethane trends, we see a different behavior with respect to the Hadar series. There is a sort of decreasing in the ethane trends between 2009 and 2016. According with the main literature, we also agree that the main driver of the ethane trends in the southern hemisphere is due to the biomass burning. And in particular, in our case, where we consider two Australian series, basically the ethane trends should be driven probably by the bushfire fire seasons that take place in Australia each year. Such that basically the common trend between the common peak between the Lauder and Wollongong series around 2016 can be probably attributed to the fire taking place in the Victoria and Tasmania states during such period. We are talking about long period fires, which account for almost 30 days. And the peak around 2006 to 2007 in the Lauder series. So this grow in the trend, this increasing the trends that we observe here could be probably explained by the so-called Great Divide bushfires, which is one of the longest fires that take place in the Victoria states during this period. With a duration of about 70 days. Well, another point that I would like to stress concern a peak that we found in the Zach species series around 2003. Let me say that this peak was also reported by the study of Frederick et al. 2020 in the study of ethane measurement in the Switzerland Alps that are very close to the Zach species station that is located in the Austrian Alps. And these peaks was attributed by the authors to the boreal forest fires taking place in Russia during such period. So we almost done. Let me just draw some conclusion. So with this study, we provide a suitable tool to investigate on the trend dynamics of the ethane time series. Let us observe that the linearity assumption is preserved in our model, allowing for an easier implementation of the analysis with respect to other other approach available in the literature. As for instance, I refer here to the nonlinear methodology proposed by Federico et al. 2020. And let me say that I mean easier in the sense from at least from a computational point of view, because in our model we have linearity. And on the other hand, we don't have any drawback in terms of accuracy of the result, because as I showed you before, we are able to derive very interesting information from the data. Finally, another important point is that our analysis suggests that ethane series may be driven by a stationary and stochastic annual cycle instead of a deterministic one. And this result is something of new in the literature, because since now the annual cycles in the ethane abundance in the atmosphere was usually treated as deterministic. Finally, in our empirical application, we found a common pattern in the Northern Hemisphere ethane series, which seem mostly, where the trend seem mostly driven by the crude oil production and natural gas withdrawals in the United States, supporting also the hypothesis by Franco et al. 2015, for which the exploitation of oil and natural gas in the United States is also affecting ethane trends in Europe. So basically, this was almost all. Merci beaucoup pour votre attention, and thanks. I finish.
Thank you very much. So that was a pleasure to hear this nice talk. Maybe there are questions or comments. No question?
Yeah, thanks a lot. I really liked the talk. Can you hear me, by the way? Because
yes.
of my headphones. Okay. Yeah, it's really interesting that you also have some different data series compared to the ones that we consider. And you have one additional one from the Southern Hemisphere, right?
Which one? You mean Izana?
The bottom right was from the Southern Hemisphere as well, right?
Oui. Yes. What you mean Wollongong? Oh no.
Yes.
Yes.
No, I think Wollongong.
Yes.
Yeah, that's interesting to see that even there is an upward trend.
Yeah, this is very interesting.
Towards the end of the sample.
Yeah.
Yeah, that's quite remarkable, because if indeed the upward trend was driven by shale gas or oil
yes, Marina,
production in the US, then this shouldn't be visible.
But here in Wollongong, we are in the Australia, so we are in the Southern Hemisphere here. Okay, what I think is interesting to observe here is the upper trend on the Thule series, no? Because we don't have an explanation for this. Because if you see in the Northern Hemisphere, all the trends after 2018 go down. But in Thule, that is near the Arctic, we have an upper trend. This is quite curious, no?
Yeah, you can still see a little bit that the upward trend has a bit of a dip, right, in 2014-15, which is a bit similar, I think, to the other series. Have you tried, or can you do in your approach, can you model them jointly? This is something that we are working on currently to see some common trends.
Okay, you mean to model the series together?
Yeah, to see if there is a common trend, maybe.
Yes, you are not working on it, but it could be a good idea. You mean basically what you mean, if I consider here my main model, you would like to assume that what is yes, that the XT here is as dimension, for instance, 6. You mean this?
Exactly,
well, yeah. Well, we think that if we try this, we should have some problem maybe in modeling the cycle, because we introduce this process just for univariate series. But of course, the idea to move on a multivariate time series should be interesting.
Yeah, this is something that I'm also working on with Simian Koopman, also maybe with state space models.
Yeah. See, yes,
so that could be something interesting to talk about.
Yeah, of course.
Yeah, thanks a lot.
Thanks to you.
Thanks you. So I don't know, are there other questions or comments? If not, maybe we just finish with the recording first.
Okay.